So yeah, light directly from the camera, from the light into the camera, and light that is direct illuminated scattered towards the camera are a major component of, or the highest magnitude, as it puts, of the stuff we get in the camera. So because those are the two major ones, we don't have to consider the full integral. We can just do a direct light to camera and a direct illumination of light to object to camera. Okay. Yep. If we don't consider indirect illumination, i.e. not direct illumination, it will be not all the light in the scene. But ambient term is like the hack that we did in early computer graphics, saying that, hey, there's just an ambient level of light everywhere because it was too expensive to do all the indirect and non-direct illumination. Anyone who's done Phong shading model will have come across the ambient term. And, it's just a constant that you add to the material or to the surface. But, so. We had a white and black raycaster where, was it white that we hit something, black we didn't? So, yeah. Yeah, the Li of X and omega hat. Yeah, and we're considering the space to be a vacuum. So we're not considering any interaction with, say, the air between the points. So it's just light in is light out because it's conserved along a ray. Huh. X minus Y between the two.
This is just direction.
Yeah. Oh, it's the we're getting the magnitude between the 2 points, or the direction. Magnitude of a normalized. That's right, because we're getting the direction X minus Y minus X. We're doing vector subtraction or point subtraction to get a vector, and then we're dividing it by its magnitude to turn that into a direction vector. So it only has a length of 1. So in here we're saying a point and a direction, and the direction has a magnitude of 1, and this is just the inverse of that direction. Okay. So 2 steps, the incoming light at X. So we shoot a ray out from X, we have to find point Y, and then we delegate is an interesting word choice there. So we need to find the point Y and then calculate the radiance excitant at Y, i.e. the radiance leaving Y towards X. So we have our intersection, and if it's not null, we compute the light leaving Y in the negative I direction, or WI direction. Otherwise, we return 0 because it didn't hit anything. Okay. So outgoing radiance is the emitted light plus the scattered radiance. Scattered radiance may have come from any direction. So emitted is like coming from within the surface. A glowing surface would emit light, whereas like a rough wood surface would reflect the light that's coming at it. Scatter it, I should say. And so we have the integral of incoming lights dotted with F, and the this is the dot product here between the outgoing ray and the normal of the surface. So this is our cosine attenuation. I'm trying to remember what F is.
PRDF?
It might be. I'm just trying to scan forward and I'm not seeing a reference to F. Yeah, probably BRDF. Yeah. It's an integral over a continuous domain because it's from all directions. It's not from a single direction. Yeah. So yeah, we're assuming away non-direct illumination by stating that the only incident light has to come from a light source, meaning our integral goes from a continuous domain to a extremely discrete one where the domain is only the directions toward the light emitters in the scene. Now that doesn't mean it's all point. I believe this model could accomplish spherical lights, but yeah, okay. Very small radii? Okay, so it sounds like we're using a point light source where the light emitter has no surface area, it's a single point. Because we say, well, the size of the surface is so small relative to our pixels and our surfaces that it doesn't matter that they have some volume. Or some surface area, I should say. Yay, underestimating radiance. Because direct illumination misses all the indirect illumination. But that's good for getting started. So all the code does is add the emitted radiance plus the scattered radiance, which we haven't defined this function quite yet. Yep. So this is where you'd add your ambient term if you really wanted to. You just add it to each surface, saying, "Hey, it's this bright." I guess. I think that probably bleed light, but this whole model is a highly assumed situation.
I think we mentioned before is like think about this as like first degree Taylor expansion of that integral.
Oh yeah, that's a very good way to think about it. So I'm just going to Euler expansion.
No, Taylor expansion, not.
Okay, yeah, I was like, wait a second. So like, we take a non-trivial f of x function that is, maybe has exponents or other crazy things in it, or signs and things, and then we just create a polynomial that correlates to it. So, x to the nth power plus the various other things. So it's a bunch of polynomials added together that behave similarly to the original, the function we're trying to simulate. And if you take it to infinity, as in you'd have an infinite number of terms, you would have the function you want. It would behave the same as, because it's an infinite series. Life isn't so nice like that, though, so we don't typically have infinite memory or time. So we have to limit our number of terms to some amount. But what Leslie's describing is, where right now with direct illumination, we're really only considering the first term of the expansion, because it is a integral over an infinite integral, not an infinite integral, but it's over a whole surface, and it would be recursive. Yeah, infinite recursion, because we're doing it at every surface and then every other surface. But by doing the direct illumination, we do the first step. Okay. This is a good understanding of what you said.
Yeah.
Yeah. Finite. That's the word I like to hear. So this is I believe this is the F that was mentioned earlier, and we're now filling it in more detail. That's okay. So because we assume a point source, i.e. zero surface area, our radiance of that point light is infinite, but it doesn't matter because it's the steradians come up again, and it's like, oh, how did that work again? I don't quite remember. So we have the magnitude of delta omega hat 0.
Isn't that just an area? It's saying that
Yeah, it is an
you're
area.
sampling an infinitely small area on the surface of the sphere.
It's an area on the unit sphere to represent its solid angle.
Right. So it's the 3D equivalent of an arc, I think.
Yeah, that's what it's supposed to be. Just
Okay.
like an angle, but in 3D.
Yeah. Oh, yeah. Well, I say arc because...
yeah, you're right.
Tomato. One can go from angle to arc and back and forth. But yeah, I guess it would be 0, since if it's if the sphere is infinitely small, then there is no surface to consider. Mm. Irradiance. So is that phi? Phi? This Greek symbol?
I honestly
Yeah,
don't know.
that's a phi.
Just
Excuse
search
me.
it.
Yeah.
If you played Magic the Gathering, you know it's a phi.
Okay, video game does teach us something.
So I have a chart.
B.
Yeah, phi, 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 fofum. Yeah. Okay. And its lowercase form is the one you, yeah. Okay. So let phi get the total power divided by a small sphere at y. Yes. All power emitted at y passes through that sphere. So at x and every other point in the sphere, the power per area to the emitter is the power divided by the surface area where we at the distance between our point x and the center y. So the biradiance, solid angled weighted radiance at x due to the entire emitter around y. Yeah, so the biradiance goes to infinity when the radiance distance goes to 0, sorry. Yes, when you get to the center point y, you get all the power. Because you approach 0 and you divide by increasingly small numbers. So yeah, we were talking about this idea last week that the total power of a point light is spread out over the shell around the center of the light, and so that we can deduce how strong the light is at distance x by taking by using the biradiance. And we just projected area. Okay. So this doodad up here would be what we fill in for beta of y comma x. And since we're now considering a distance omega, where does the s come from? Is that the scattering function? Oh yeah, because we want the strength of the light. So our integral goes from a continuous one to a discrete sum of every light, and we get the strength of each light, and we have our scattering. Was it s that is our scattering function? Using the notation. What is this? Hopefully it'll explain it. I'm not following this paragraph here.
I feel like you
Is it-
read too quickly because I'm also not fluent.
Okay, so I was confused about where this S function comes from. Did that get mentioned above, and I just glossed over it? I think that's just like the scattering function, the scattering of the surface. But then we're dotting it with the normal.
It's
Someone want to speak?
no. I thought I had the answer, but I don't.
Oh,
I'm just as confused.
Maybe it's about the surfill.
Oh yeah, I think it's S is for surfel, and it's the surfel at that point.
yeah. Because we have the projected area, and that would describe what a circle refers to. Yeah. So, I'm gonna zoom out a little bit so I can read the whole thing. So the biradiance is also equal to the integral of the small solid angle by the source at y about x. So is it talking in this description? This is like describing the tiny solid angle that where around the sphere at point y in to the point x, and it's like the small area we're considering. The source has bounding radius. R is much less than y. That's the absolute value, so that's just the.
What's the PP3 link? Is that a link to something?
It is, and it's the notes, or it's the. It's showing up as direct illumination hashtag PP3. I think it's like in the references. Oh. And it would be one of these?
What the fuck?
I like the free URL. I appreciate that. Illumination for computer generated images. This is the Fong paper. Oh, it says thesis. Yeah. And the link's not working. It's like this was Fong's paper here was like one of the. His thesis was one of those that took all the previous research of the last 10 years and put it in a format that when everyone went, oh yeah, this is how we probably should be moving forward. And the Fong shading model comes from it. Why? In a similar way to Veitch's thesis, and who's the other guy that does path tracing? Kajia. I think it's Kajia's thesis.
I'm not aware Kajia has a thesis that is famous. I know there's a paper, but
I don't want the Jim. Okay, that's understandably thin because he's a researcher in a field, and outside of that, maybe I'm just going off a bad memory of something. Yeah, I don't want to purchase this thesis. Can I like? Okay, maybe. This name is like. Kajia is a name that I know of because I've been told it's important.
It's the rendering equation guy.
Oh. See?
yeah,
that is important.
We read his paper before in this meetup.
Yeah? Yeah, it was just a paper. Okay. And I think Veach's thesis is a thesis.
Yeah, it's
Maybe I'm
like
thinking of something
10
else.
page versus like 200 page or something. So
Of which
definitely.
invariably 20 or 30 of those pages is pure padding. But we won't get into that kind of thing. So it's definitely abuse here because we assume the light and the surface are far away, so it's not a curved surface but actually flat and constant over the domain. Okay, so we've done a bunch of math. Let's see how we implement it. So to calculate the scattered radiance at a circle towards a direction.
Towards the eye.
Yeah. We have our emitted radiance, so our built-in emission. We get our position in our normal. So x is our position, n is our normal. And for every light, we get the position of the light, and this is just asking for an XYZ coordinate of it. And then this would trace a ray and detect if the point is visible, so the path between x and y is unobstructed. If it is unobstructed, we get the vector towards y from x. That we get that direction. We calculate the biradiance at point x from the light. So this light has all the information inside of it to calculate the biradiance given point x. And then we call the finite scattering density function to get the color given our outgoing and our incoming directions. And we dot product our incoming light by our normal. We multiply it by f, which we still really haven't defined, and then we multiply it by our biradiance to get the illumination from that direction. And we just do that over and over for all the lights. So, okay. Visible biradiance. Just return that visible always returns true. Just assume that it returns true. Yeah, that's a easy thing to assume. Yeah, so the scattering function f, we don't have a good model for that yet, so it's just f. So he just does finite scattering density, and it's a black box. You put in some directions, you get an f out of it, and you plug it in and be happy.
F is
So-
basically just gonna divide by pi. Like it's just a Lamb version PRDF. So you can just
Yeah, it's
can
just
just-
lab
it's-
version.
Yeah.
yeah, it's a bit of a trip, like trying to understand like why you divide by pi, like why that's good enough. I'm still not sure why. It's a little bit crazy. But if you don't divide by pi, essentially your material is going to be too bright, and apparently it means you're not going to be energy conserving. But why pi exactly? I don't know.
What's the surface area equation for a sphere? 4/3 pi r cubed.
Yeah, if it's a unit sphere, it's just 4 pi.
Oh. Oh, I'm thinking volume then. Sphere surface. Yeah. Yeah, 4 pi r cubed. And for a unit sphere, r is 1, so it's just 4 pi. But it is odd that it's just pi and not like 2 pi or something, because we're considering the hemisphere, not the sphere.
You should try Googling for Lambertian BRDF y divided by pi.
BRDF y divide by pi. Hey, there's a game dev. But the Computer Graphics Stack Exchange seems like a good place to start. This person answers their own question. Because cosine of theta integrates to pi over the hemisphere and not 2 pi. The incoming line is multiplied by cosine theta and the BRDF. That's very unsatisfying.
There's also another answer that's a little bit different. I think if you add like a intuition or whatever to your search.
Oh.
I think it's just saying that if we cosine pi comes from the Lambertian term, it's like that dot product in the integral. And if we consider that, then
I think this is what? I was thinking this was here's Scratch Pixel. And I don't know if it's referring to the same thing.
Yeah, it's the same thing.
Oh, okay. So this seems like it would actually prove it, why that's the case, rather than just saying that is what it is.
Yeah, you can. It's.
I think it's just we have integral that need to be 1, and then we just use some derivation to conclude at the end we need to divide albedo by pi.
Okay. I will take your observation for that. Yeah, it has to do with energy conservation. Y is a bit muddier than just.
It's definitely like an approximation. Like it's not, because there's like BRDFs that will do like a diffuse inversion that is more precise, and they do like way more calculations. Like I forgot the name, but there's another one. It does way more than just divide by pi, but it's like way more expensive, and the result is really not that different. So like
I see what
We
you
talked
mean.
about that like last week, but I forgot the name.
Yeah, okay. So and this is really just describing making up your own scattering function.
This is for diffuse, so everybody uses Lambertian, but for later on, he's probably going to explain like for specular. And for specular, you could use Phong or the super complicated other ones.
Yeah. Error is acceptable. Yep. Unacceptable. Okay, so we now have to define the visible function to make shadows work. So yeah. what I said earlier. If X and Y are there's stuff in between them, it's in shadow or not visible. Got the binary function. And if there's a set intersection on the line segment XY, then it's 0 and 1 otherwise. Yeah. Raycasting from so yeah, we just do raycasting like we did before. The difference is instead of having surface calculations, it's just a simple binary hit something or didn't hit something. And so we're adding in our visibility function v of y comma x, which pretty much is just a multiply by 1 if we hit something, multiply by 0 if we didn't. I mean, if we didn't hit something, multiply by 1, and if we did hit something, multiply by 0. So the contribution of that light in the sum is negated. Not negated, but canceled out. Canceled out? Made 0. Yeah. So what's the exercise is to implement this scattering density function on your own, which seems like you just need to figure out what rho is and divide it by pi.
Rho is literally just the color of the surface.
Oh.
It stands for albedo color.
Yeah.
It's literally just your
Yeah.
texture color.
Yeah. That makes sense. Spectral reflectivity P. Rho. Not P. Did that. Ambient illumination. Because we don't have shadows. No, because we don't have indirect illumination. We want the ambient term to add some light into the scene at every point. Yeah, that was always fun, is having to manually monkey around with the ambient lighting term to get things looking right. Yeah, ambient doesn't have any information about the environment other than a constant factor. So, of course, it'd miss reflections from the environment.